Okay, this is to try to get us caught up and back on speed for what we should have done in class today. We needed to cover radicals that needed to be divided, and then the other thing was how do you convert between a rational exponent to a radical exponent, or excuse me, to a radical form, and then radical form back to a rational exponent. So that's the two things I'm going to try to accomplish in this video. So this is from the packet that I gave you guys last week. If you don't have that with you, you can print this off from Blackboard under class sessions. And I am going to do a few of these of each type, and then I will be assigning some to complete and bring on notebook paper the next time we have class. So looking at when we're dividing with a rational, okay, there's some properties that we can use. The first thing is, I'm going to make this a 1 out front so that you can kind of see this. If you have no adding or subtracting connecting things, notice this is all multiplication and division, then you can split this into two separate pieces. This is 1/5 times radical of 15 over square root of 20. And because these are both under square roots, we can actually make it one big square root. The reason I want to do that is because I can then simplify this fraction inside this radical. So this would be 1/5 times the square root of, divide them both by 5, this would be 3 over 4. Now, I would then split it back up into a radical on top and bottom, because if I do that, I can then take the square root of 4. So sometimes putting things together and taking them back apart helps us to simplify. Square root of 4 is 2. So now I'm just multiplying. 1 times the square root of 3 is just square root of 3. 5 times 2 is 10. So this is square root of 3 over 10. Now there's another way to approach this, and it's called, so this was just using properties. Just using properties. So breaking it up into two fractions because it was multiplication and division, and then just using the fact that I can put two radicals that have the same index. Now if this was a cubed root and a square root, we would not have been able to put them together. But since they're both square roots in one fraction, we can make it one big radical. That allowed me to simplify and then break it back up to simplify again. So I'm going to do this same problem, but I'm going to do it a different way. This next way is called rationalizing. One thing we don't like when we're dealing with square roots is we don't like them to be in our denominators. So one way to get rid of that is to make that square root into a perfect square. Now the way we do that, if it's a square root, you just multiply it times itself. That's one way of doing it. But that actually is not the most helpful, because that will make this much bigger than it needs to be. But you could do that. Since it's a square root, you can just multiply it by the square root of itself. Another possibility is to find the first perfect square something goes into, or you could reduce first and then do that, because 20 does have a perfect square in it already, but it's not going to get rid of the complete radical. So what I think I'm going to do here is ask, what does 20 go into that's a perfect square? 20 times 2 is 40, 20 times 3 is 60, 20 times 4 is 80, 20 times 5 is 100. And 100 is the square root, when we take the square root of 100, it's 10. So whatever we do to the bottom of a fraction, as long as we also do that to the top, it is legal. So we're multiplying, and that's only for multiplication or division. You can't just add stuff to the top or subtract. So what we do to finish this off is we actually multiply what's here. So square roots get multiplied together, things outside get multiplied together. So this would still be a 1, and then square root of 15 times square root of 5, I believe that's going to be 75, but I'm going to double check myself. Yeah, so square root of 75 over 5 times the square root of 100, and notice that there's a perfect square on top as well. So square root of 25 times square root of 3, because that would be what makes 75, and 25 is a perfect square. The square root of 100 is just 10. We can take the square root of 25 and get 5 on the square root of 3, over 5 times 10. Notice I didn't multiply the 5 and 10 together because I noticed that I was going to get a 5 that was going to cancel out. So notice in both cases I was able to get the square root of 3 over 10. Now, if it's something that you can easily just reduce, I would not go the rationalizing route. For example, number 2, you don't need to do anything with the denominator. It's already a perfect square. So this is going to be square root of 8 over 10 if I reduce that out. So now I no longer have a radical in the bottom, but I do need to worry about the top. 8 is the square root of 4 times the square root of 2, and I picked those numbers because 4 is a perfect square. Square root of 4 is 2 on the square root of 2 over 10, and this time when you reduce, you have to make sure you reduce the outside pieces. So this is 2 divided by 2 is 1, so I just have 1 on the square root of 2, which you don't have to write the 1, it's understood to be there, and 2 into 10 would leave me with 5. So square root of 8 over 100 actually reduces to square root of 2 over 5. So notice that it was not helpful to me to make this 8 over 100 and then reduce because I already had a perfect square in the bottom. Okay, let's look at another one. In this case, you might want to put it together because 4 goes into 20. So there's different, like I said, there's different approaches and they all should usually give you the same answer. So that would be square root of 20 over 4. So this is 3 over 2 times square root of 5. And remember that would be over 1, so this is 3 square root of 5 over 2. I could have just as easily gotten that by pulling a 4, square root of 4 out of this and a square root of 4 and then canceling those, or actually evaluating the square root of 4s and then noticing the 2's would have canceled out. So, you know, there's multiple approaches you can use to these. Let's talk about another one where we have to rationalize. Since there's no radical on top for number 5, I have to get this radical out of the denominator. So the best way to do it, if you don't know, is just multiply a square root by its matching square root. And the reason for that is if it's square roots, that creates a perfect square. So this would be square root of 25, which we know is just 5. So notice I no longer have a radical in the denominator. I want to do a little side note problem. So notice that if it's a cubed root, so things like 2 over the cubed root of, let's say, 4, that is not a perfect cube. 4 is not a perfect cube. And if you multiply it by cubed root of 4, that doesn't guarantee it's going to be a perfect cube, because 4 times 4 is 16, and that is not a perfect cube. So when you're dealing with perfect cubes, you need to ask, what is the first perfect cube that 4 goes into? So remember, my perfect cubes are 2 cubed is 8, 3 cubed is 27, but I already know that 4 goes into 8. So if I multiply this by a 2, that will make a cubed root of 8 in the bottom. Whatever you do to the bottom, you have to do to the top. So this becomes 2 on the cubed root of 2 over the cubed root of 8. And we know the cubed root of 8 is 2 on the outside, and then the 2's would cancel out. So I wanted you to see at least one where you don't have the perfect squares. So if it's perfect cubes, you can't just multiply by itself. You have to think what would make it a perfect cube. Okay, let's do maybe 1 or 2 with some variables in them. And in fact, 11, 12, and all the rest of these are going to be something in the next section. So don't get upset about those yet. I'm not covering them on this video because they're not going to be on the actual test for this unit. They'll be on the next unit because the radicals kind of overlap between the two groups. So look at this one right here. All right, if I wanted to rewrite this as 2 different fractions, since this is all times and division, I could write 1/4, and then I have a big radical that says 3x squared y cubed over 5x y cubed. One reason to do this is that you might get something to cancel out. So notice this x, one of those cancels, but I would still have one left with this, and the y cubes are gone completely. So what I'm left with is a 1/4 and a square root of 3x over 5. Now we want to get rid of that square root of 5 in the denominator, so we need to multiply top and bottom by the square root of 5 again. That's called the rationalizing step. So I get 1/4, and then my second fraction will be square root of, that'd be 3 times 5 is 15x. Square root of 5 times square root of 5 is square root of 25. So I have 1 on the square root of 15x, and this is 4 times 5, because square root of 25 is 5. So we get square root of 15x, because we don't have to write the 1, over 20. Now check a couple things. This is in a radical, this is not. So you cannot reduce the 15 and the 20 because they're not in the same state. One's under a radical, one is not. The 15 has no perfect squares that go into it, so it's staying under the radical. And x is to the first power. This is a square root. Remember, as long as this power is smaller than the root, you are good. So this is the final answer. Okay, so those are all the ones that we need to do for this section. So the ones you're going to be responsible for turning in to me, and I will type this in the announcement I send as well, is number 3, number 6, 7, 8, and I want you to also try 10. Okay? So I will type those up with the announcement that I send when I finish the video. Now, let's talk about the other piece that we were supposed to cover today, which was rational exponents and how they relate to radicals. So I'm going to my notes. These are the notes that are also in Blackboard, just so I can show you the definition of this. Rational exponents are exponents that are fractions. For example, something like x to the 1/3 power. This is a fractional exponent or rational exponent. This is really a radical. It's just in a different format. The way this works is that the denominator is always the root, and the numerator can go one of two places. It goes with the variable, but it can also be outside of the whole thing. So I'll show you what I mean by that. So if I want to change this, this would be a cubed root of x to the first. Okay, so that is the conversion between, this is called the rational form, or sometimes just positive exponents. That's sometimes what they'll say in the definition. And this is called the radical form. Okay, now if I had something like x to the 2/3, so notice the top number is no longer a 1, you can write that as cubed root of x squared, where you keep the 2 inside, or another equivalent way is to do the cubed root of x and then square the whole thing. These are both equivalent, and depending on what's inside here, you may not want to square it first. If it's a perfect cube, you may want to take the perfect cube and then square the answer. So as long as we're dealing with real numbers for our exponent pieces, then this is going to work. Okay. All right, so that's kind of the background information you need to know. So I'm going to pull up the worksheet for this section. Okay, so this first part of the direction says write each in radical format. Okay, it doesn't say simplify, it just says write them in radical format. So for this first one, this would be a square root. So we don't have to write the 2, but you can if you want. And it would be 7 to the first power, so square root of 7. For this one, it would be cubed root of 2 to the 5th. And again, they did not ask me to simplify. So if they said simplify, I would need to work this out. I'd have to do 2 to the 5th and then try to take the cubed root. For this one, it will be the square root, because it's a 2 on the bottom, of 6 cubed. Okay? So if all you're doing is converting and you don't see the word simplify, you're just showing me how to change the format. So this one wants me to go the other way. If you have a power on the outside, remember that's really related to the numerator, and the radical is related to the denominator. Okay, so this would be 10 is my base, and I'm on the 3, 2, because remember that square root is a 2. This would be, my base is 2, and this is to the 5/4. And for this one, this is a 1 inside, so this would be 2 to the 1/3 power. Okay. Now, this is a little bit more complicated. Let me see how far I want to go. We'll probably do the simplifying ones in class together. So let's do write expression in radical form. So we're trying to convert these to radical form. Now I wanted to point out, if there's a parentheses here, that means this whole thing is in the radical. Okay? If there's not a parentheses, it is not all in the radical. So that means that you would have pieces that are inside versus pieces that are outside. So let's just work on this one first. First of all, you don't want a negative exponent. So the first thing I would do is move the whole thing to the denominator and change that to the positive 5/4. Then I would convert that denominator to a radical. This would be the 4th root of 5x to the 5th. Notice I kept the 5x in its parentheses because both of them would get the 5th power. Another way of writing that same thing would be the 4th root of 5x with the whole thing raised to the 5th power. So either one of these would be acceptable. Now again, they did not ask me to simplify. If they asked me to simplify, I would have to try to figure out how to get a radical out of the denominator. And like I said, I'd rather do those together if we can. So then this one right here is the square root of 10n to the 3rd. It's already got a positive exponent. So one way of writing that would be like this. Or we could write square root of 10n all raised to the 3rd power. Okay, I'm not going to worry with this one because we won't give you anything like that on the test. The reason is that you have to convert that back to a fraction yourself. And then our last group I want to do on the video is these say change these back to exponentials or exponents. So this would be m to the 3/4. This is a 1, so v to the 1/4. And notice here, this is all under the radical, so that means it's going to be in a parentheses, and this would be 4/3. Now I did want to distinguish what's the difference if it's not in a parentheses. So let me go back up here. I'm going to add a different one for number 17. What if we'd had 3 v to the 3/2? Notice this is not all in a parentheses, so that means the 3 is not really connected with what's going on here. This only connects to the base directly in front of it. So this would be the square root of v to the 3rd power, which again could be simplified, but if you don't have the parentheses, only the base in front of it goes in the radical. And say here that I had, 3 and then the cubed root of a to the 4th. Notice that in this case only the a is underneath, so this would be a 3 and then an a and 4/3. So notice the parentheses distinguishes between what's under the radical versus what's not under the radical. And for now that's going to be enough because I think I'm not 100% sure. I'm not going to still have the stomach bug tomorrow. I will let you guys know as soon as I feel like I can make that decision. So I will do these on this last 6-ish on the video if I have to, but I'm going to try to hopefully be there tomorrow and we can do those in class plus the last page of the packet. But just keep checking announcements for that update. Oh, and for this page, I'm not going to make you do all of them, but I'll circle like every other even. So I want you to do number 2, and this will be on your own notebook paper to turn in, 6, 10, and 14, and let's go ahead and add in 16 instead of 18. I don't want to give you 2 negative exponent ones. So I'm going to post this video to the YouTube channel and then I'll send out the announcement with the information and the numbers that need to be completed as well.